I've been working on this Ben Eater style 6502 computer with the intention of hooking it up to a world's worst video card. But in my world's worst video card revisited videos, you'll know that I introduced hardware scrolling, and I want to be able to attach that video card with the hardware scrolling to the 6502 computer. To do that, I've needed to hook up some flip-flops to use as register. So these are D-type octal flip-flops. This chip, and this chip are 74 HC 273 octal flip-flops. And this chip is an 74 HC 138 decoder. And I've got this hooked up so that it resides at address 5000. Just like with Ben Eaters, there are other addresses that will work with it. Basically, any address that has a 1 or 0 in the the most significant bit of the address, a 1 in the next significant bit, a 0 in the next, or anything in the next significant bit, and a 1 in the next significant bit after that. So 0, 1, anything 1 will address this chip. But the important thing is that it can be addressed in a way that does not collide with the address at 6,000 and many other addresses for the 6522. So this is addressable. And it allows you to address up to 8 different addresses. So they start at 5,000, but you can do 5,001 through 5,007. And each different address sends one of these pins low. So if you address 5,000, this pin here is sent low. 5,001 is this pin. 5,002 is this pin, and so on, all the way down here to 6th pin here, and then there's one on the other side to create a total of 8 different addresses that it can have. And so it has 3 address lines, which I've wired up to A0, A1, and A2. And to show that these are working, I've created a relatively complex set of things for it to tests to test the output. And I showed you those tests with just this signal register. And here you can see them running. And here you can see it tells you what it's done. So here it's doing a rotate ping pong test where the bits go back and forth, then alternate bits test, and then rotate bits test where it just rotates in one direction. And in doing this, I ran into something that I found quite interesting and difficult to understand. And in fact, I haven't figured it out completely. I want to show you what I've done, and I'm hoping someone watching this could tell me what it is that's going on here. I'm new to a 6502 assembly language, and this is totally messing me up. So here's the program that I have running. And it just starts with setting up some 0-page definitions. So these are locations that are going to be used for variables. There's the value that I'm going to be storing to the registers in 00. A wait time, which is used for a timer, is stored in address 01. A cycle, which is the number of times that each item has run, is stored, or each test is run, is stored in cycle. You can see each test runs 5 times. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So that's stored in cycle. Message is the message where we're going to store the address to find the message that you see displayed on the LCD. And then PP direction, that just keeps track of when we're doing the ping pong test, keeps track of whether we're going to the left or to the right. Then I've got the register set up, register 5,000, 5,001, 5,002 for the 3 different registers I have. And again, this one is at 5,000, and that's hooked up to these LEDs. This one is at 5,001, and that's hooked up to these LEDs. And this one here is at 5,002, and that's hooked up to these LEDs. And I'll show you why I hooked those up to LEDs, even though I'm not running tests on them currently. So this is the vectors, where the vectors begin for the 6502 at FFFA. This is the start of our ROM at 8,000. This constant is the number of cycles that we want to do, and you can see it's 5. That's why we're doing 5 cycles. These are the LCD controller bits. Those are used for the LCD controller, of course. And then I begin the beginning. So I originate at ROM at 8,000. And then I've got NMI, IRQ, and reset all pointed to this beginning location at 8,000. And so I begin by do the standard. I load FF into X register, and I transfer X to S, and that starts our stack pointer at the top of the stack. Then I load a value for the init wait timer. If you remember, there was a where we keep track of how long we've been waiting. This loads a value and then calls a subroutine called wait. And the wait subroutine is very simple. It just loops through X and Y consecutively for a total of 65,536 cycles, or loops through. And then it also loops outside of that as a loop for the amount, whatever you passed into wait time. This is sufficient to give us a wait of several microseconds to several seconds. So it's good enough for the purpose of what we're doing, but it is not fancy. Then we jump to the LCD init, and this just initializes. This just initializes the LCD the same way that Van Eater does. The only difference is I turn the cursor off. So right here, this is a 0 instead of a 1, so the cursor's off. Then I go into the main program loop, which I've labeled as such, and I begin by jumping subroutine to LCD clear, and this just does the clear command for the LCD. So there you can see that it's all, I push A, I load clear display, jump to subroutine, LCD instruction, and then pull A, and then return to the subroutine. Then I load X with the low order of alt bits message, and that's way at the bottom here, alt bits message. Here I've got the message for the 3 different tests that I run. So that's where that is. And then I load the high, so I load X with the low order, and I load Y with the high order. And then I run to jump to print string, which will print that string. So I input, so here you can see I input X and Y are the where we put in the low order and high order of our message location. And so I store X into message, and I store Y into message +1. And then I load a 0 into Y, having stored it. I don't need it anymore. And then I load A with this is called indirect indexed addressing. So what this is this says take the location stored at message. That's the location we just stored there, and then add Y to it. And so we do that, we load that, and if we load it as 0, then that's the end of the string. So then we jump down to done, and we return from the subroutine. Otherwise, we jump to subroutine to print char, and that's the print character subroutine that Ben Eater wrote. It's exactly the same. We increment Y, and then we jump back to print, and we keep doing that until we load that 0. So it's important that the strings have the 0 at the end. Of course, we've used the ASCII Z directive, which guarantees that there'll be a null or 0 at the end of the string. So that's how print string works. And this is working fine. And this is going to be the source of the problem that I'm coming to you with. So let me get back to that. Let me just go through quick. I load the even number bits and store them at the register, and then I wait. And then I load the odd numbered bits, and I store those in the register, and then I wait. And then I loop until I've counted cycle time. So I decrement the cycle. That's decrementing the value that's at the address cycle. And then I branch. If I haven't gotten to 0, I branch back to the alternate bits test. That does the alternate bits. The rotate bits is similar. So here I just print, I print the rotate bits message to tell you what it's doing. And then I load cycles up with a 5. And I load the register to have a register value to have no bit set. And then I load the register value, I store it to the register to A, and then I wait a little shorter time for this, and then I rotate left the register value, and when I branch until you get to a 0, at that point, you've rotated everything, and then I decrement cycle and I start again. So that's that test. The ping pong test is a little bit more complicated. I'm not going to go through the whole thing this time. I'll be happy to if somebody's interested. But basically, what it does is it uses rotate left and rotate right, and it doesn't rotate everything completely off the end, if you will. Testing, testing. Testing, testing. Why does the pause button do nothing? All right, where was I? All right, so basically I just rotate left and right based on the PP direction, PP underscore DEIR, which is the ping pong direction. And I change that back and forth when I get to the end, and I do that cycle times, and then from there I loop back to the first test, and we just keep doing that. So that's I don't want to go over this because that's not really the source of my problem, although it sort of is. I'll explain momentarily. So here's the thing. So you can see that this code is working fine. Let me make this minor change to it. I look at this print string subroutine, and I think to myself, it'd be better if we pushed A onto the stack because we're going to screw around with the A register. So let's push that on the stack. And when we're done, let's pull it off the stack. That's all, just that change. So let's compile that. There we're compiling it, and then we should program it. So put the chip in the programmer and write it out. Now we put the chip in the computer. And press reset. And now you can see it's doing this weird thing. It's filling my LCD screen with commas, and it's not updating the register at all. And in my investigation, I found what I suspected, which is it's not returning from the print string. It's not returning from the print string subroutine. So I'm going to, let's try, in my investigation, I found sort of what I expected, which is that it's not returning from the print string subroutine. And so what I'm going to suggest we do is that we take advantage of the fact that I have 2 extra registers wired up, and I have LEDs wired to them, and I'm going to use those as a way to display what is being returned from the stack. So let's start with let's see, go back up to print string. Let's start with putting the code back to where it works. So this code works. Then what I want to do is I'm going to pull the return address off the stack, and I'm going to load it into the register so we can see it. So how you do that is let's pull A, and then let's store A in register 2, and that's going to be the low order byte of the address. And then we want to save that so we can put it back. So we're going to transfer A to X. Then let's pull A again, and let's store this. This will be the sorry, that was the high order. This will be the low order address. So let's put that in red 1. Store A to register 1. And then let's just push that right back on. And then let's transfer X to A. And then let's push that back on, and that puts us back into the state that we were before. And let's compile this, and we will see if that works. So put the chip in the programmer, and let's write to it. Then we'll move the chip back into the computer. The power to clear the screen. And there you can see, let's run it again. And there you can see it's working. And you can see that the high order address that it is returning to, that's interesting. It worked and then it stopped. I don't know what to make of that. That's the right address, but it is not returning. Let's see if I did everything right here. I'm pulling A. Oh, here's the problem. Push A. All right. You guys probably caught that before I did. All right, let's put that fixed code in here. And write that. Then let's put it back in the computer and start from scratch and run that. And there you can see it's interesting. It says it's doing the alternate bits test, but it's actually doing the ping pong test. But this return address is more or less what I expect. At least the upper part of it is 8,000. We'd expect that. And it looks like the bottom is 1,4. It's actually not what I expected this to do. I thought this would work correctly. Thought this would. It's interesting because it seems to be jumping back to a place that puts it into the ping pong test. So that's more weirdness. Let's look what happens if I put the if I pull A here, and then I push, and then push A here, push A, and then if I pull it here, this will be the A. This will be whatever's in the A register when I pushed it. And then what we'll do? We'll transfer A to X or A to Y because we're not using the Y register anymore. And over here we'll transfer Y to A, and that should be the equivalent of what we were doing before in terms of pushing A, pulling A, and then restoring it at the end. And then this happens in between. Let's see what happens there. So compile, and then program our flash RAM. Put it back into the computer and reset. And so this is interesting. So this is, I think, very strange in that, it does get through it, prints it, and then look at the address that's returning here. The high order byte of the address is 8001. So where does that come from? That's what I really don't understand. The low order byte looks the same. The high order byte is changed. Oh, and now it's jumped into the ping pong. Huh. Might be because I touched something. Oh, I don't see how touching something down here would have done that. Eventually it goes back to 800 and we're in the ping pong test and it's staying in the ping pong test, which is very strange because following the ping pong test, the only thing I can suggest is that the ping pong test maybe is has whatever was an A in it now. Or no. Oh yeah, hold on. Here it has hung up again and it's back to 8001 for its return address here. So it sits and does that for a while, and then it goes to the ping pong test. It never gets to where the code prints out that it's going to do the ping pong test, though. So that's what's going on. That's my problem. And I was hoping that someone out there would watch this and could help me understand why just adding this to adding push A, pull A at the beginning and end, just like so, why that would cause this to stop working. Oh, and here's another strange thing. It causes it to stop working in the current code. But let me show you this. If I go back up to here, and in the ping pong test, I get rid of most of it. So let's comment this out. So this is all it does here is load the register value, store the register value. It doesn't do anything else now. Now this is going to move the location, which seems to be important. I'll show you that in a minute. The location of print string is going to be moved up. And if I compile this, at least it has been working. So let me, we'll write that. And now you see that it is doing the alternate bits test, rotate bits tests, and back to the alternate. Oh, and not doing the ping pong test, of course, because we skipped that. We commented most of it out. So yeah, it's very strange. I'm not storing anything to the registers anymore, so these don't mean anything. They're just whatever happened to be in the register when we reset the computer. But here that's working. Now let me show you something else. If I go down to before print string and I just do, just put some filler in here. So ASCII Z, let's put some X's here. This won't run as code because it's between the subroutines. It's just a filler taking up space. And now if I compile this and write to the flash RAM, as you can see, it gets through writing out the characters, but now it's back to not doing what it's supposed to. So it has to do with where it is in memory. I can get rid of some of these, like so. Writing it to it. Put it back. And now it works. I have tried. I thought it seemed to have something to do with memory. I've tried swapping out the flash RAM. That made no difference. I also swapped out the static RAM, and that also made no difference. So these are actually new chips, and they, from what I was using, and they are doing the exact same thing. I'm still open to the idea that something I've done in here where I'm starting to work on configuring it to work um, with my world's worst video card. I'm open to that being part of the problem, although I can't figure out. I've done some control logic here towards these other RAM chips, but they're not actually wired in. So some of the addresses are wired, but the data isn't wired in, and so there's no way that this is like colliding or anything. I'm just I'm at a loss. So I'm hoping someone can help. And I appreciate any help anybody can give. I also appreciate anyone who's watched this video to the end. And if you like what I'm doing and you wanted to subscribe, that'd be great. Also, if you'd click the like button, that helps me out a lot. And I hope to talk to you all again real soon. Thanks.